Okay, so welcome to question 7. Question 7 reads, an enzyme catalyzed reaction was carried out in a 0.2 molar trace buffer. The pH 7.8. As a result of the reaction, 0.03 molar hydrogen ion was produced. So to understand this, we'll start by writing the equation for this. So this would have meant that we had a trace acid plus some sort of a base, which can be water, a weak base, to produce the trace conjugate base plus the hydrogen ions. So the first part of the question says, what was the ratio of a trace acid to a trace conjugate base, and hence the concentration of these at the start of the reaction? So we'll start first by finding the ratio. To find the ratio, we need the pH and the pKa value. The concentration of the trace and the trace conjugate base we don't know. So we know of the pH of 7.8, and the trace buffer has a pKa value of 8.1. So we can use the Henderson-Hellsberg equation to calculate the ratio by saying the pH is equal to the pKa plus the logarithm of the conjugate base divided by the weak acid concentration. So if the pH is 7.8, then the pKa value is 8.1, then what will be the ratio of the trace base to the trace acid? So this will mean that we'll have 7.8 subtracted by 8.1, so 8.1 will be equal to the log of a fraction of the trace base divided by the trace acid. So 7.8 minus 8.1 gives us a negative of 0.3, will be equal to the log of the trace base over the trace acid. So this means that we are going to have the trace conjugate base over the trace acid concentration be equal to 10 to the power negative 0.3. So this will give us the ratio, the trace base over the trace acid, to get 10 to the power negative 0.3 gives us a 0.50. So this is the ratio, a ratio of 1 to 0.50. So this is the ratio, or this ratio can be written as a 2:1 ratio. This is the ratio. We are done with the first part of question A. Then we can calculate the concentration of the tris base and the tris acid at the start. So the initial concentration of this will be, we know that the concentration of the tris base plus the concentration of the tris acid will give 0.2 molar. From the question, the buffer had a 0.2 molar. So if we combine the base with the acid, we get 0.2. Or if we mix this, we get this concentration. We can make this as the subject of the formula. The base will be equal to 0.2 molar minus the concentration of the tris acid. Okay, so this can be written as, we have three equations here. This is the third equation. This is the second equation. Then we also had this. You can write it as the first equation. So using this equation can help you to find the concentration of this. So if we replace the base in the first equation, the tris base, we will replace 0.2 minus the concentration of the acid divided by the acid is equal to 0.50 as in equation 1. So write that the tris base is 0.2 molar subtracted by the concentration of the tris acid divided by the concentration of the tris acid is equal to 0.5 or 2/1. Right, 0.5, which is there, which was our ratio. So now we can work out this to get 0.2 molar minus the concentration of the tris acid equal to 0.50 concentration of the tris acid. We collect like terms. 0.2 molar is equal to 0.50 tris acid plus 1 tris acid. So we get 0.2 molar is equal to 1.5. If we add 0.50 plus 1 tris acid, we get 1.5 concentration, 1.50 concentration of the tris acid. Now to find the concentration of the tris acid, we need to divide this by 1.50. Also here we do the same thing, divide by 1.50 divide by 1.50. Okay, we have 1.50 there. So if we divide here, we'll have the concentration of the tris acid equated to 0.2 molar divided by 1.50, you get 0.133 molar, since it's a concentration. Then having the concentration of the acid, you can also find the concentration of the base using the relationship we formed of a base plus an acid equal to 0.2. Now you have the concentration of the acid. We said it was a base plus an acid gives us 0.2 molar. Then the base plus acid of 0.133 molar is equal to 0.2 molar. Okay, so that will give us the trace base equal to 0.2 molar minus 0.133 molar. So the concentration of the trace base will be 0.067 molar. So these are the initial concentrations of the base and that of the acids. Initial concentration. You can get them with 1 if you want. Yeah. So that was question A, 1A. Then part B was asking what were the concentration of the trace acids to trace base at the end of the reaction. So at the end of the reaction resulted with a 0.3 molar acid. So from this equation, we added the acid. So if we add the acid, this by the Richard-Terra's principle, this will increase, then the acid will decrease. No, actually this one, sorry. So this one, the base will decrease by the amount of the acid we are going to add, and this one will increase. This one will increase. Okay, this one will increase. So what we are talking about is this the trace acid with water from the trace base plus the proton. So if we add the proton here, this one, the base will start to decrease. We'll be using much of the base to convert it into an acid. So the initial concentration, let's say initial concentration here, initial concentration of the trace acid was 0.133 molar. Then that of the base was 0.067 molar. So if we add the proton to this base, we are going to decrease it by that concentration of the proton, which is 0.030 molar. Then this one will increase by 0.030 molar. Then you can find the actual number of moles, or rather the concentration of the acid and the base at the end of the reaction. So if you subtract, if you add 0.13 molar plus 0.03 molar of the proton, we'll get something like 0.163 molar, that is of the acid, and of the base you subtract 0.067 minus 0.03, you get 0.037. These are now your final concentrations after the hydrogen ions were produced. That was all with question B. Then question C was asking what was the pH at the end of the reaction. So to find the pH, we still use the Henderson-Hertzberg equation by saying the pH, this is part C, pH is equal to the pKa plus the log of the trace base divided by the concentration of the trace acid. So the pH, we're looking for the pH after adding the proton. Before we added the proton, the pH was 7.8. Now if we add the proton, the pH will change. So the pH, we're looking for the pH will be equal to the pKa value is 8.1 plus the log. The concentration now of the trace acid, now the trace base, the new concentration is 0.037 divided by the concentration of the acid, the new concentration at the final, it will be 0.163. These were the concentrations of the acid and the base. So we can find now the pH by saying pH is equal to 8.1 plus, so the log of 0.037 divided by 0.163 is negative 0.644. So you add that, you have a pH of 7.46. So the pH has decreased. At first it was 7.8. Now upon adding the proton, it had to reduce to 7.46. This is evident that we added the proton. The last part of this question was what will be the final pH if no buffer was present? If this buffer, the trace acid, the trace base was not present, what will be the pH? We only added the proton without the buffer. So we'll just use, and this is part D, the pH will be calculated by just saying the log, the negative log of the concentration of the proton we have added. And that pH will be negative log of 0.03. So the pH will be equal to the pH, so negative log of 0.03 will be 1.52. That is the pH. Now this pH is very acidic. This pH is very acidic compared to the buffer, which has a capacity of the ranges of 7.5 to 8. So if this pH was present, we would destroy the enzyme. Since we're dealing with the enzyme will be denatured. So this was question 7. Thank you guys.